Hello everyone. In the previous class, I was discussing about the fundamentals related to dynamic analysis of the problems using finite element method. So here we have some numericals related to the dynamics, that is finite element formulation of dynamic problems. So the very first numerical is calculate the eigenvalue and eigenvector for the matrix A is equals to 4, 1, 1, 2. For this, it is required to have the standard the characteristic equation, that is A minus of lambda into x is equals to 0. So we have A, that is 4 1 1 2 minus of lambda, unit matrix, that is lambda into I is nothing but the unit matrix, which is 1 0 0 1 into x1 x2 is equals to 0. So the non-trivial solution, which is determinant of these two matrices, which is 4 minus of lambda, 1, 1, and 2 minus of lambda is equals to 0. So when you have this characteristic equation, which comes out to be lambda square minus of 6 lambda plus of 7, and when we find the lambda 1 and lambda 2 value, it comes out to be 1.58 and 4.41, where lambda 1 is 1.58 and lambda 2 is 4.41. So these are the corresponding eigenvectors are obtained. These are the eigenvalues, and we can obtain the eigenvectors by applying the equation 1 for each reason, that is lambda and lambda 1, lambda 1 and lambda 2. So first of all, we will substitute lambda 1 value. So when you substitute lambda 1, it comes out to be 2.42, 1.42, x1, x2 is equals to 0, 0. So we are wanting to obtain the eigenvectors eigenvalues, eigenvectors corresponding to the first eigenvalue. So therefore, it comes out to be 2.42 x1 of 1, because we are finding the first modal shapes, plus of x2 1 is equals to 0. And from this, x2 comes out to be minus 2.42 of x1. So therefore, the value of x1 is considered as unity, and value of x2 in the first mode shape, it comes out to be minus 2.42. Similarly, when you use lambda 2 as 4.41, in a similar way, we will get x1 as 1 and x2 as 0.41 in the second modal shapes. So like this, we can solve the problems of eigenvalues and eigenvectors. So another problem, find the eigenvalue and eigenvector for the stepped bar shown in figure when subjected to axial vibration. Take two finite elements. So we have a stepped bar, length of each member is L by 2. X modulus is E, area of the first step is 2A, area of the second step is A, and density of the material is rho. So the characteristic equation here is K minus of lambda into M is equals to 0. So K1 is A1 E1 by L1 in the matrix of 1 minus 1 minus 1 1. We have the area for the first step as 2A E L by 2. So when you simplify, it is 4AE by L in the matrix of 1 minus 1 minus 1 1. So element 1 is connected between node 1 and 2. So it is written over here as 1 2 1 2. Similarly, for element 2, it comes out to be 2AE by L in the matrix of 1 minus 1 minus 1 1, and it is connected between node 2 3 2 3. So when you add together, the global stiffness matrix is A by L in the matrix of 4 minus 4 0 minus 4 6 minus 2 0 minus 2 2. And globally, there are three nodes with 3 degree of freedom system 1 2 3 1 2 3. So here we have to have the mass matrix, which is the consistent mass matrix, which is M1 is equals to rho 1 A1 L1 by 6 in the matrix of 2 1 1 2. So we have rho value, area value, length value, and we substitute it. So globally, M will be equals to rho A L by 6 in the matrix of 2 1 0 1 0 1 by 2 0 1 by 2 1. So in other words, we get a standard mass matrix equation. So what we need is K and M. So when we substitute the K matrix and M matrix, so this is the characteristic equation we get. And applying the elimination method of boundary conditions. So looking at the problem, it is a simple problems again. Node 1 is fixed. So eliminating the first row and first column, first row and first column of the stiffness as well as mass matrix. So the remaining equation is this. So dividing throughout by AE by L, so to get cancel this. So therefore, this term, it is lambda rho L square by 12E is considered as alpha. So we will left with the 6 minus 2 minus 2, 2 minus of alpha in the matrix of 6, 1, 1, 2 is equals to 0. So when you subtract these two matrices, we will get this. And when you simplify this, we get quadratic equation of alpha square minus 2.54 alpha plus of 0.7272 is equals to 0. And when you simplify this second order equation, we get alpha 1 as 2.22 and alpha 2 as 0.33. And we know the value of alpha as we have substituted this entity, this term as alpha. So we get lambda from this, and the lambda 1 value, when you substitute alpha 1, we get it as 26.64 E by rho L square. And when you substitute alpha 2, we get lambda 2. And correspondingly, we know that lambda is equals to omega square. And omega square is therefore 26.64 E divided by rho L square. So omega 1 will be 5.16 square root of E by rho L square, which is the first natural frequency. Similarly, you can use the alpha 2 to find out the lambda 2, and thereby you can find the omega 2 value, which comes out nearly, which is equals to 2 in the matrix of square root of E divided by rho L square, which is the second natural frequency. So we can find the eigenvectors similar to the previous problem, wherein we can substitute the values of lambda in the expression. So when you substitute, we can get the value of x2, x1 and x2, as well as the x2 and x3. So the model shapes x1, x2, x3 for this problem. For the first mode shape, what we get it as 1 and minus 1.5 of x2, and for the second mode shape, we get x2 is equals to 1 minus 172. So similar to that problem, the second problem, we can find the three-stepped problem also. So I will not go in detail in this. So this is the way we have to solve the dynamic problems. Even this problem also, we can have the solution for this problem similar to the previous problem. So hope you can solve these type of problems without having any problem. So thank you very much for watching this video.